All right, welcome back, NPCs. Today we are going to go ahead and jump in to 3.2. And we are going to be talking about the physical and chemical properties, which I would shorthand like all of this if I were you, but it's your choice, of water. Now, we've already talked about a bunch of different things. Remember, water is a good insulator. It does some crazy stuff with densities as you, get colder, which is really unique to it. Naturally shows up in all three states on our planet. The three states of water, what are they? Gas, liquid, solid. What's the fourth state? Plasma. Cool. All right, so we are looking at these guys. Now, just so you know, a lot of this stuff are things that we deal with over there. So remember, everything that we do, whether it links directly to work at the hatchery, every single part of it is going to be related, at least lightly, with the salmon that we're growing over there. So, checking it out. There's a lot of chemical and physical properties of water. The physical properties, we've talked about a few of them, and we've hit on other pieces here as well. But we're going to jump right in with some physical properties that I think we've already addressed. And here we go. I need to start as we make the transition to being more formally in the book. Worksheets or book questions do you prefer? Okay, I'll make worksheets for us. We're going to start getting a little bit more work on the academic side, just so you guys are prepared for it. We'll keep going over there all year long, though, just so you're aware. Cool. So, physical properties, as we're looking at it, there's a lot of them. Water's pretty unique in a lot of different regards. The first physical property that I want to kind of discuss is transparency. What does it mean if I say water is transparent? It's clear. Transparent just means you can see through it, right? As compared with other words. Now, this is important. So I'm just going to say water, biologically, clarity of water is important. Biologically, clear water is important. Now, why? Why would I care that water is clear from a biological point of view? Well, I don't care if I can see through stuff. I can't see my cells directly. I'm that came off. There was a bit of snark in the tone. That wasn't I'm trying to devil's advocate against your statement. Talk with your neighbors. Why does it matter, biologically speaking, for life on our planet that water is clear? Give about 60 seconds. Talk it out. Okay. Do we live in the water? No. Do we breathe? Now, our air has something really important in it. Oxygen. Cool. Where does most of the oxygen that we breathe all the time come from? Interesting. How? Trees is a natural thought. It's wrong, just so you know. Yep, trees make a lot of oxygen, but it's not the bulk of it. Definitely not. What lives in the ocean? Oh my gosh, that's what I'm looking for. Obviously fish, right? Whales, sharks, all those things. Whales aren't fish, just for the record. Is there algae and plants in the water? And is there more water on the surface of the planet or land? By a lot, right? 70% of our surface is water. Which means, do you think there's more plants in the water or on land? In the water. Which means there's these huge populations of aquatic plants and algae and all this that wind up producing a ton of oxygen for us. We need this fact because you guys have all taken Bio 1. Plants eat sunlight, quote unquote. And they eat sunlight and carbon dioxide, and they turn it into what? Energy. And then this is just an analogy. Plants obviously don't really eat, right? They also don't poop or pee. But if we think about they eat light, what do they poop out? Oxygen. Their byproduct is oxygen. Now, as we look at this, that whole process of taking sunlight, eating it, turning it into energy, and then getting rid of oxygen in the process, what's that whole process called? Photosynthesis. Synthesize as in you're creating. Photo as in a photon, which carries light. We get photosynthesis. Our air quality is super dependent, and don't misunderstand. Trees matter. the Amazon rainforest does a huge job of like carbon sequestration. It takes in a lot of carbon dioxide, which is why like illegal logging and agricultural destruction of forests is such a big issue because we destroy them all. However, the same issues are present within the ocean as well. Now, as we go through here, weird ideas that I think we've talked about, and as much as I want to go into the physics in part of it, we're just going to do a little subsection. We're going to talk a little bit about sunlight. All right. When we look at sunlight, and this is a weird question because I'm not asking you what color is the sun. What color is light? Light is white. That was a much faster answer than I was expecting you guys to come up with. Cool. I was expecting yellow because the sun is yellow. But if you put a different filter on, just look at different stuff. The sun can look dark red or light yellow or white, or it doesn't matter. As we look at it, check it out. White light leaves the sun. White light emits from the sun. How long once a photon leaves the surface of the sun? Do you guys know how long it takes to get here? 8 minutes. Once a photon is ejected via nuclear processes in the middle of the sun, any idea how long it takes for it to get from the center of the sun all the way out to the end, like to the surface of the sun? Like millions of years. It's crazy. The photons all bounce around. They get stuck. There's weird stuff that happens. Anyway, white light emits from the sun. Now, kind of interesting idea here. White light, we look at, we see it all the time. This isn't white. You'll notice there's a big white spot here. Can you guys see all the different colors? Okay, if I spin this, any idea what it's going to look like? Let's check. Does it look kind of white to you? Now, if you like stopping and look really close, but obviously we're just combining all these colors because our eyes can't catch up. White light is comprised of different energies. And again, we're not a physics class, I'm sorry. When you think about the UV spectrum, first thing, I say UV spectrum, you guys know what I'm referring to. Okay, what's the lowest energy? We're just testing your physical science stuff. There's a lot of different radiation. The electromagnetic spectrum is what I meant to say, not UV. Are we getting blasted with radiation right now? 100% yes, absolutely. Where? What's causing us to get blasted with radiation? The sun, but I'm kind of protected from the sun. So there's UV light. I don't think I'm getting hit by UV light right now. But I am getting hit by light. And this, like, legitimately is electromagnetic radiation. It's no different than the scary radiation, except one key difference is the amount of energy that it contains. So I'm getting hit with this, right? Are we getting hit by any other sources of radiation? The light's above, certainly. We're getting hit from some light from outside, so there's some radiation coming from there. Any others? The screens, sure, so it's still white light. It's visible light that I'm getting hit with. Is KUCB broadcasting right now? I bet the radio waves are passing through us right this second. I guarantee it. Do you feel it? No, you don't. None of us do. They're really low energy. We don't feel it. We don't interact with it. Now, as we go through here, there is a whole universe that we just never get to see. We see like 1% of all possible light. Human beings, that's all we can see. Now, night vision cameras, they see a slightly different spectrum. They look at infrared, so below red, lower energy. Follow-up question. What are the colors of the rainbow? Roy G. Biv. We get, I'm just going to write it, R for what? Red, O for yellow, green. What's indigo? And violet. Now, these are the colors of the rainbow, and I can't do it without hearing my kid's toy that he hasn't played with in a while, but new kids' toys, if you haven't heard them, they kind of slap when the music they play. They're pretty good. Looking at it, of these, are you worried about getting burned from infrared light? Have you ever had that concern? How many of you guys wear sunscreen? Like, not every single day. That'd be silly. I mean, maybe you should, but if you're on vacation down south, do you wear sunscreen? You should. Like, I definitely need to. You probably need to as well. Huggins, I would assume that you need sunscreen pretty regularly. Depends on the sunscreen. It could. Now, looking at this, what I want to just make sure that we have is, check this out. As we look at this as a continuum, and it really is, we have this little tiny part of the electromagnetic spectrum that we get to see. We have most energy over here. most energetic or energized, energy, which means we have least energy over here. Okay. Now, here's just an interesting question. White sunlight leaves the planet, or leaves, I'm sorry, white sunlight leaves our star, right? The sun. It hits our planet. Cool. Like, I'm glad it does, because otherwise we just wouldn't happen, which, bummer. Here's an issue that I see, though. The most energetic light should be what? Or is what? Violet, which means like anything above that, like higher energy or ultra energy, ultra meaning above, you start to get to UV where you start to worry about lights. Just little like health plug. Even if you have a dark complexion and you don't sunburn, you should wear sunscreen. You can spend a little bit more money and get the natural mineral sunscreen so you don't have to worry about the weird additives that they put in. But every single person here should wear sunscreen because dark people get skin cancer too, just so you know. Okay, now looking at it. Does sometimes light hit the ocean? Like all the time, right? Like literally all the time there's sunlight hitting the ocean. Different oceans, right? Because the earth spins. What color is the ocean? Now that's kind of a weird question, right? Because water is clear. The ocean shows up blue. Why? Because it's the light. Okay, now I'm going to propose something, and this is a really weird result, and I wish that we had the physics and the ability to go into it. But if we look at the ocean, and I would encourage draw it. If you want colored pencils, you can. I have beautiful color here on mine. You don't need it. But let's check it out. Here's the surface of the ocean. Okay, I can't draw it clear, so I'm just going to use this. Now, the sunlight hits it, for sure, guaranteed. Do you guys remember earlier this year when we talked about how deep does sunlight penetrate the ocean? Any idea or remembering of what that distance was? About 100 meters is the average. Realistically, you don't get to like no light until past 200 meters. It just gets really dark. But here's a weird result, and it's up to you guys how you want to draw this. When we look at these, and I'm going to try my best. I'm going to need you guys' help because pink and purple and violet and stuff, they all blend together when I look at it. What color would you call this? You know what? We'll start here. Okay, that's red. I got that one. I know that one. Red light, most energy or least energy? Least. Roy G. Biv, we start with red. Below that is infrared. Okay, so when white light hits, it gets split by the atmosphere in a variety of different things. It hits the water, right? Okay, it gets separated into its component parts. I want you guys, and we're going to do this together, red light, hypothetically, penetrates to about here. Okay, I'm going to move on to orange. What would you expect to happen? What's going to penetrate? Will it penetrate deeper than red or less deep than red? Deeper, why? It's more energized. Okay, do me a favor real quick. Be prepared to erase this. Roughly, and for real, I can get you colored pencil if you want them. If you use the regular ones, just show me without a depth actually given. Everybody agree that orange goes a little deeper? More energetic, right? Cool. Finish the other 5 colors. Show me where you think they penetrate depth. I'll go back up. Roy G. Biv. And logically, I would agree with you 100%. I'll tell you it does. Why does it make sense that yellow light would penetrate deeper than orange light? It has more energy. Now, beyond that, we're going to see just some wonky things that happen here. How about green? Deeper still? Okay. Now, my guess, and I don't want you to sketch this, and I'm just making up the distances, just so you know. I'm just doing it arbitrary to show that one goes further. I have a pretty good feeling that you're going to say this happens. I don't know where I would find indigo. Is it this color? I just don't even know. Is it this?
Yeah, I did purple.
Isn't that? That's purple? Yeah. Where do I get indigo up here then? That just looks purple. Like all these look purple. That kind of looks pink. All right, so check it out. That's all right. Indigo. Okay, and then logically speaking, it would seem reasonable that violet, which I think is just a fancy name for purple, goes here. Everybody probably has that picture drawn, right? Okay, here's a weird thing. No. It does not work this way, and it's crazy. Out of these, and I'll show you guys a video of this. I struggle to remember if we looked at different videos in here. Out of these, I would say since red goes deepest, if you cut yourself underwater, can you see red in your, like, does it bleed red? Anybody ever cut yourself underwater?
Yeah.
Did we ever look up a video of people bleeding underwater?
Yeah. No.
Oh, it turned blue. Wait, purple. Wait.
Fish blood is green when people spearfish down deep. Now, it's not really green, but there's something weird going on. Okay, looking at this, all the red light stops penetrating at this depth. And I can give you guys the depths here if you really want. About 10 meters is all it takes. You will not see red anymore once you're down past 10 meters because red light doesn't penetrate, which means you won't get red light reflecting. You won't see the color red. Okay, now this is a natural thought to what should happen. And this is what my intuition tells me should happen. Unfortunately, in this situation, my intuition and your intuition is wrong. This does happen. Up to here, everything's normal. Now, all of a sudden, once we get to indigo, which I'm just going to use, is indigo lighter or darker than purple? We're just going to Google this really quick because
When you grab a clutch and you're like, oh, this is blue. Oh, wait. It's lighter. No, that's
we're going to Google it real quick. We're just going to see it. I don't want it on YouTube. All right. There's indigo. Dark blue. Dark blue is indigo. Okay, here's dark blue. Okay, what really winds up happening is something more like this. Now, as we look at it, this is a super weird idea and it's a weird result in my mind. There's a lot of this that bothers me, and when I'd never seen this before last year when I did ocean science stuff. I'm sure I've crossed paths with it at some point, but I just don't recall being weirded out by it. Why would this possibly be the case? And I know it's a big question. It's even when I tried to do it, looking through scholarly research and stuff, I couldn't find a way to pose this question in a way that made it nice and contextually make sense. Good ideas, bad ideas, don't care. I want ideas. Why would this possibly happen is a thought at hand. Again, you have no idea, but I want just answers. Shot in the dark. Why would blue light penetrate deeper than violet, knowing that violet has so much more energy? Talk it out. I don't have a definitive answer. I've spent a good amount of time trying to find a definitive answer because it bothered me that I didn't know, but it bothered me much more that I couldn't learn it after the fact. But there is a misconception that I make that's just not quite true. When we look at this, if we think about it as a single one photon having to pass through, then maybe our kind of intuition, our gut feelings would be correct. Here's the thing though. These lights and these wavelengths that produce these colors of light are not equally distributed as they enter our solar system, as they enter our atmosphere. Which color of light do you think is most present in white light? Go way out on a limb here. If we just think of photons, just photons in general, which are what carry light. White light is made up of, let's say, 1,000 photons. If I say that, cool, out of 1,000 photons, 100 of them are red. Do you think there's more orange or less orange? More. Do you think there's more yellow or less yellow compared to orange? More green or more yellow? More blue or more green? Okay, this is going to get weird. More blue or more indigo?
More blue.
More blue. The highest amount of light, the most common frequency out of the white light that comes from our sun as it passes through our atmosphere winds up being the frequency that produces blue light. There's more blue light to travel deeper. There's way less violet light, which means it doesn't have as much kinetic energy as it travels, and it doesn't penetrate as deep. Okay, it is a weird idea. That's the really brief, really brief answer. We're just going to put a little justification in blue right here and say, this is cooler, but it's also the most concentrated. Yes. Yes, go for me too. Cool. All right. This is the most concentrated type of light that comes out. Because there's more blue light hitting the ocean than anything else, What light do you think reflects off the ocean above all other colors? Blue, and it's why our planet looks blue as we view it. Cool. As we're looking at stuff, we have an opportunity. Yeah, and it's awesome. Now, as we go through here, this is all related to the clarity of water, which is like the kind of big idea that we've been going around throughout. As we move forward, we're going to sneak in a new word here. So a little bit of continuation. It didn't happen, right? Like nothing. Agreed? Cool. All right. So looking at this, see, now you kind of get a kick out of it though, right? Like at least a little bit. So all of you who are really judgy a minute ago think that's the dumbest thing I've ever heard about the forks. If you find any of this entertaining, we're on the same page, whether you like it or not. Cool. Dwayne, every single person switched spots. Except Jim in. Yeah. Cool. All right. Now, in perfectly clear water, this is what holds, which means only H2O. How much of the water that we see in our oceans is only hydrogen and oxygen? So let me rephrase that. You pick a bucket from anywhere in the ocean and you look at it under a microscope or you analyze it chemically. You're going to find hydrogen and oxygen for sure. That's the H2O. Will you find other stuff? Guaranteed, if you're in the ocean, what are you going to find? Salt. You're going to find salt. Now, when we talk about the salt that you're going to find in the ocean, what sort of salt? Sodium chloride. Awesome. Now, you're going to find some others as well. Like you're going to find contaminants and things like that in smaller amounts. But it all comes down to this. As materials, and we're just going to say, yeah, as materials, it's just really vague. As materials dissolve, which remember, water is the universal solvent. So lots of solutes are present in the ocean. As dissolve. There we go. What happens with the clarity of the water? So less clear water, would you agree? And that's a weird way to word the question. As materials dissolve, water gets less clear. Now, depending on the concentrations, it can be hard to tell. If I had a glass of water in front of me, 2 glasses, and one was saturated with salt, meaning no more salt can be added, but it's all dissolved, and one was fresh water, could you tell just by looking at it? Do you think you could? If I had a cup of pure water and a cup of 1% saltwater solution, would you be able to tell the difference just by look? Not a chance. Not a chance. Would you be able to taste 1% salt content in your water? Very, very, very much. Okay. Cool. Now, there's a word for this. When we talk about the clarity of water, we're going to sneak this in. This idea is something that we do have a way to test for, and there's a couple different ways we can do it. We are talking about the idea of what is known as turbidity. Okay, turbidity, not skibidity. Turbidity is how clear water is. Now, that's kind of subjective, right? Because really clear water, we can all agree when water is really clear, but if I said, oh, how murky is it? That's a hard thing to measure, right? 2 ways to do this. We can do this, and we will do this digitally with intensity of light changing over a distance. And these are pretty sophisticated ways to do it. You can see, and I don't know exactly what the units come out to. We'll have to look at it when we do the play around with it. But murky water, light travels less far through. So if we see how much energy is lost, there's one way to do it. The other way to do this is a lot more subjective, but it's much more common because it's cheaper and they're really easy to make and find. We can use what is known as a Secchi disk. S-E-C-C-H-I. Is that right? I think so. A Secchi disk. Now, you guys have gone around and I imagine snooped, for lack of a better word, not in a bad way, around the hatchery. Like you've looked at a bunch of stuff over there. Has anybody come across the long tube that has a black and white circular thing on the bottom? I bet you have. When I show it, we'll see it. Okay, if we look at a Secchi disk, we have some. This thing. There's a long tube over there with this on the bottom. Okay, I'll show you guys. It's not even hidden anywhere, but you might not have come across it. Now, if we wanted to measure the turbidity, we're not going to get like a really awesome unit out of it, but here's the deal. High contrast is easy for our eyes to pick out. If you put this in clear water, you could probably drop it like really clear water, 100 or 200 meters, and you'd still be able to pick it out. However, in murky water, it's going to change drastically, right? The murkier the water, or the more turbid, you could say, the less deep you're going to be able to tell. We can measure it just using this. And it's literally as simple as just taking a disc, just like this, is connected to a rope. You just drop it in the water until you can't see it anymore, and then you mark off and see, oh, I could see this far into the water. Now, it's not a real nice unit, but it is there. Okay. Cool. Sweet. Moving on. We're going to be talking a lot about these dissolved things. We're going to go a couple more minutes, and I'm going to make you guys brainstorm my fish poster ideas a little bit more. Sweet. One more thing that I want to talk about. And there's a lot of, gosh, there's so much cool stuff. This could be physics just all the way, but it won't be. Okay. Beyond that, anybody, who in here is a good swimmer? You don't know how to swim?
No, I do. He does not. I do.
Okay. Well, jumping into the deep end doesn't prove it. Swimming in the deep end will prove it. But, no, I believe you. I taught one of my best friends. I had several, like, almost want to say dad moments with him, where I just taught him how to, he was an older friend of mine, taught him how to ride a bicycle. We were like 17 and 18. We just had a really busy summer. Taught him how to ride a bicycle, taught him how to ride a motorcycle, taught him how to swim. Just total dad moments over and over when I was in high school, which is kind of fun. Oh, yeah. His name is Loon. All right. Okay. For those of you that can hold your breath well, how deep down do you think you could swim? You couldn't swim 100 meters. I don't believe you. How many of you can, at the pool, swim down to the bottom of the deep end and touch it? Sure. Okay. Or even with your feet. Do you notice anything as you go deeper and deeper and deeper? Oh, the pressure. Okay. Now, we're going to talk about pressure. And I wish I had some David Bowie queued up and ready to go. Again, the sense of humor that's just not going to click, but that's all right. Some of you might get it. Okay. Right now, are you being pushed on by the air? All the time, right? Now, pressure is a weird idea because remember, everything is made of little tiny particles that do what? They wiggle or buzz or however you want to word it, right? Everything is always buzzing and moving. Now, all my stuff that's buzzing and moving is stuck to me, thankfully, through like some pretty fancy fundamental forces. The air is not all stuck to each other. Do you feel the air pushing on you right now? So you might feel a draft, but in still air. Oh, somebody said still water was the other one. It was something I was supposed to say, but I don't quite get it. In still air, if you're in a room, there's no draft at all. Do you feel the air pushing on you? No, not at all. Is it pushing on you? Yes. Any idea how strong it pushes on you? 14 pounds per square inch is how hard you're being pushed on. Every part of your body. Hold your hand out right now. There's 14 pounds. Pick a little square on your hand. 14 pounds of air pushing here. Now, what's weird about this, and it's not weird when we talk about it here, there's air above, right, that's causing this pressure because there's like thousands and thousands and thousands of meters above us. That's all that weighs up. Okay, now, everybody, like we're just going to say it's a statement of fact. 14 pounds of pressure pushing right here. How much is pushing right here? The exact same. It's the same from the bottom, the top, the side, everywhere, because all those particles are just buzzing this fast. Doesn't matter if they're hitting from here or from here. They're all hitting in the same spot. Now, the same thing happens with water. We're going to say that pressure is just how hard the fluid, which, just to clarify here, fluid, not necessarily liquid. Air is fluid, just so you guys are aware. Like, this is fluid right here. It's just like water, but it's way less thick, right? Okay, how hard the fluid pushes on an object. And I'm going to say pushes on a submerged object. Okay, weird parts about this, and it seems so weird to me, and it's probably weird to you guys, but I think we can clear it up. Pressure, when we talk about it, it is the same from all directions. Okay. Now, when we talk about pressure here, and we've talked a little bit about the flow of energy, the universe wants balance. Whether it really wants it or not is a hard thing to try to talk about. But the universe, if it wants balance. Hot moves to cold. Okay. High energy always moves to low energy because they want to balance it out. When we look at our area, we're pretty windy here, right? Why? Like the natives called this the birthplace of the winds. I don't know the word in Unangan, but birthplace of the winds is what Dutch Harbor and Unalaska has been known as. Why does the wind blow so hard here? So you might think because there's no trees. Turns out might play a little role, but it's not a huge factor. Could have to do with the water. You said pressure. What about the pressure?
It's like, there's like high and low, but right around there.
Yep, so we live in a region where we experience what are known as the Aleutian lows. We get really big low pressure systems that move through for a variety of reasons. Around us, there's a bunch of really high pressure systems. The universe wants what? Balance. If we have a bunch of high pressure 20 miles away and we're really low pressure, all that high pressure air needs to move directly to us. Now, if you haven't checked windy lately, yesterday was beautiful. We were in the eye of the storm. It looks like we might be kind of chilling out now, looking outside. But check it out. We'll just see these small little pressure differences. Right now in Unalaska, we have 984 somethings. We'll talk about these somethings in a second. It's pretty chill right now. Looking over here, we just had this high pressure front move through us, 974. So a little bit lower, I'm sorry. We are out of our super low pressure. These little differences are what cause all this wind. When you look at a hurricane, and it's really misleading, hurricanes down south, when you look at them, they're nowhere near this size geographically. Like, they're tiny. However, when you look at the differences in pressure in the storm and outside of the storm, much larger gaps here than this. And it happens for sustained periods of time. Now, same from all directions. And I want to look one little table, a couple more things. You know what? We're going to talk about pressure tomorrow. 5 minutes. Get me good fish pun or play on words relating to volleyball. There's some work to be done, and it's nearly there with net and setting and all those things. Oh my gosh. We set net is like such an easy, I don't know, there's stuff there. More than just net, you can talk about setting the net. Don't be silly, let's get gilly. All right.